So in Chapter 6, Section 5, we're going to be talking about some properties of logarithms. Before we do, I want to remind us of some properties of exponents. So let's talk about some exponential properties. So if I multiply two things with the same base, so if I have x to the a times x to the b, what do I do? We're going to add our exponents. So when we multiply two things with the same base, we add their exponents. So like x squared times x cubed is x to the fifth, because we add the 2 and the 3. We also have, this is our product rule for exponents. We also have the similar rule for when we divide. So if we divide two things with the same base, what is it we do with our exponents? We subtract. So we get x to the a minus b. And this is our quotient rule for exponents. And then we have one more rule, which is if I have x to the a raised to the b, if I have a power raised to a power, I multiply the exponent. So that gives me x to the a times b. And this is called our power of a power rule. So the reason I'm bringing up these exponential properties has to do with the fact that logarithms are exponents. So the log properties that we're going to introduce, or the properties of logarithms, are really just these three properties. But if we remember, logarithms are exponents, the logarithms are going to do what the exponents do, because the logarithms are exponents. All right, so let's go ahead and take a look at our first log property. So if I have the logarithm base a of a times b, well, if I multiply two things together with the same base, that's my first property up here, what is it that I do with the exponents? We add them. Logarithms are exponents, so this becomes 2 logarithms added together. So that's our product rule for logarithms. Similarly, we have a quotient rule for logarithms. So if I have the logarithm base a of a divided by b, if we divide two things with the same base, what do we do with the exponents? We subtract. So then this is the logarithm of a minus the logarithm of b. And that's our quotient rule. And lastly, if we have the logarithm of a raised to the b, then if we have a power raised to a power, what did we do with the exponents? We multiplied them. So b is an exponent and the logarithm is an exponent, so we multiply them together. And that's our power of a power rule. So in each of these cases, we note that the logarithms follow the pattern that the exponents follow. So in our product, we added the exponents. In our quotient, we subtracted the exponents. And in the power of a power rule, we multiplied the exponents. Remembering that logarithms are exponents, they do exactly what they're supposed to do. So printed at the top of our notes, there is a summary of some of our logarithmic properties. There's also some properties we haven't talked about yet, but we will. But they're all summarized here in this table. We'll do the change of base formula a little bit later today and some of the other ones, but this is just a summary of all of those rules. All right, so let's go ahead and do our first example. All right, so we want to express log base c of 5x as a sum of logarithms. Well, we have two factors inside of our logarithm. So then by our product rule, the 5 is going to be our m, and the x is going to be our n, and multiplication turns into addition. So we get logarithm base c of 5 plus the logarithm base c of x. So that's our product property for logarithms. We take each factor and it turns into a logarithm. And when we have products, they turn into addition. All right, so applying our product rule twice, we end up with, this is a natural logarithm. So we get natural log of x plus the natural log of y plus the natural log of z. So we would have our 3 logarithms, each of them for each factor. All right, so our next example we want to express as a difference of logarithms. So we need to be a little bit careful though, because this is a mixture of two different rules, right? So in the numerator we have a product, and in the denominator we also have a denominator, so we have a quotient. So as a way to help us check if our answer is correct in the end, if an exponent is in the numerator, it's positive. If an exponent's in the denominator, it's negative, right? So when we do our quotient rule on this first part, so when we use our quotient rule, we're going to get the logarithm base c of xy minus the logarithm base c of z. We can then expand using our product rule. Let's just do it vertically. And then we use our product rule to split up the x and the y. And we would have the logarithm base c of x plus the logarithm base c of y minus the logarithm base c of z. Well, notice in our final answer, the x and the y were both in the numerator of the fraction, and they are both positive logarithms. The z was in the denominator, and the logarithm with the z is negative. All right, so we start once again with our quotient rule. And that's going to give us the natural logarithm of x minus the natural logarithm of y, z. And we're going to use our product rule on the second logarithm. So we have the natural logarithm of x minus, we have the natural logarithm of y plus the natural logarithm of z. But that minus sign belongs to both of those logarithms. So our correct answer should actually be the natural logarithm of x minus the natural logarithm of y minus the natural logarithm of z. If we look at our original problem, which variable was in the numerator? X, and that logarithm is positive. Which variables were in the denominator? Y and z, and both of those logarithms are negative, right? So these parentheses, or forgetting that that negative here belonged to both the y and the z, it can be easy to forget that. So we can always use that idea as a parity check. Variables in the numerator are going to have positive logarithms. Variables in the denominator will have negative logarithms when we expand. All right. Let's take a look at our next example. So instead of monomials, we have a mixture of monomials and binomials. So we identify each of our factors. So I have a factor of 24. I have a factor of x. And then I have a factor of 5x minus 9. So I'm going to have three things just like we did in U-try number 1. So I'm going to have a logarithm with a base of 7, 24, plus a logarithm with a base of 7x, plus my last logarithm, a logarithm still with a base of 7, and this time I have 5x take away 9. So the key thing there we have to be aware of is that we have a product rule. Products mean factors. So each factor gets its own logarithm. So note that this is not true. You can't have the logarithm base 7 of 5x take away 9 does not equal the logarithm base 7 of 5x plus the logarithm base 7 of negative 9, right? So this is false. So we can't break up logarithms over addition and subtraction. We can only break up factors inside of logarithms. All right, let's take a look at our next one. So example 4. We got something similar happening once again to what you had in your U-try. So we've got a mixture of both the product rule and the quotient rule. So how many factors are there present inside of this logarithm? Yeah, 6, right? We've got the 21, we've got the x, we've got the x minus 2, the x minus 3, so 1, 2, 3, 4 in the top, so in the numerator. And we have two factors, the x minus 3 and the x plus 1 in the denominator. So that's a total of 6 factors. Based on the observation that we made up here, the ones in the numerator are going to be positive, and the ones in the denominator are going to be negative. So let's write this out. We'll have the natural log of 21 plus the natural log of x plus the natural log of x plus 2 plus the natural log of x minus 3 plus, nope, ran out of stuff in the numerator. So now minus the natural log of x plus 3 minus the natural log of x plus 1. So in this process, we use the quotient rule once and the product rule 5 times, right? And that would give us this in expanded form. So we have our rules, and we can write them out one by one by one by one, and if you have to do that for a while, that's fine, but we really don't want to have to write out 6 different rules just to expand this, right? We should be able to look at it and pull our factors apart based on the product and quotient rule. All right, the next rule that we need to talk about is our power of a power rule. And so our power of a power rule said if we have an exponent, we can multiply, if we have a power raised to a power, we multiply our exponents together. The net effect of this is the exponents come down in front and become a coefficient on our logarithm. So log of x to the 7th power is the same as 7 times the logarithm of x. All right. All right, so doing the exact same thing, we're going to swing that 1/2 out in front. So we get 1/2 times the natural logarithm of x. So a natural logarithm of x to the 1/2 power is 1/2 times the natural logarithm of x. So we need to recall a fact of a couple of things. So the first fact is x to the 1/2 is the same as the square root of x. In general, we have the fractional exponent rule. And our fractional exponent rule says the following. If I have x raised to the a divided by b, this is the same as the bth root of x raised to the a power, or the bth root of x raised to the a power, the a on the outside. So the a can either go on the radicand, on the inside of the radical, or the a can also become an exponent all the way on the outside. So in general, a fractional exponent, a divided by b, is we take the bth root of x raised to the a power. We can also use this in reverse. Any radical can be written as a fractional exponent, which will be the way we will have the most use out of this exponent rule. All right, so let's take a look at each of these. All right, so we want to expand the logarithm of x squared plus y squared. So which rule can I use? Well, do I have any products? Nope. Do I have any quotients? Nope. And I don't have a power on the entire argument of the logarithm. So this cannot be expanded. Because we don't have any rules that apply to sums inside of a logarithm, right? They have to be factors, quotients, or exponents on a monomial. We don't have a rule for exponents on individual terms in a binomial. So this one can't be simplified. All right, let's take a look at example 7. We want to write this as a product. So the first thing we need to observe is our fractional exponent. So we have a square root in the numerator. So we're going to have the square root of x minus 3. Or sorry, not the square root. We have x minus 3 times x squared plus 4 squared, and that whole thing is in the square root, right? So that square root becomes to the 1/2 power, all divided by, in the denominator, 5x take away 4. So before I even start using any of my logarithm properties, I can use some of my exponential properties. So if I have a power raised to a power, what do I do with my exponents? Well, I'm going to multiply. So that gives me the natural logarithm of x minus 3 to the 1/2 times x squared plus 4, but its exponent is a 2 and a 1/2, so 2 times 1/2 gives me 1, because that's 2 times 1/2, right? And then in my denominator, I still have my 5x minus 4, and I'm going to put it in parentheses just to emphasize that it is a factor. Okay, so now I have 2 factors in the numerator and 1 factor in the denominator. So I get the natural logarithm of x minus 3 to the 1/2 plus the natural logarithm of x squared plus 4 minus the natural logarithm of 5x take away 4. Finally, to finish up, I swing my 1/2 out in front. And I get 1/2 times the natural logarithm of x minus 3 plus the natural logarithm of x squared plus 4 minus the natural logarithm of 5x take away 4. And that would be my fully expanded logarithm. So the key observation that we want to take out of this is that sometimes when we are resolving our logarithmic properties, we may need to use our exponential properties as well. So in this case, I had a product raised to a power, so I multiplied each of the elements in the product's exponents by the power, and to expand before using our logarithmic properties. All right. So the first thing we're going to need to do to resolve this is use our fractional exponent rule. So we rewrite it as the logarithm base a of x to the 6th over p to the 5th, q to the 8th, all raised to the 1/2. And from here we actually have 2 choices. So you can either swing the 1/2 out in front and distribute it in at the end, or we can use our power of a power rule. Personally, I think that's easier, but you get the same answer either way. It doesn't really matter. So if we multiply each of the exponents by 1/2, 6 times 1/2 gives me x to the 3rd. 5 times 1/2 gives me p to the 5/2, and 1/2 times 8 gives me q to the 4th. So now I have a product and quotient rule. P and q are both in the denominator, and the x is in the numerator. So I get the logarithm base a of x cubed minus the logarithm base a of p to the 5/2 minus the logarithm base a of q to the 4th. And then we move all of our exponents out in front. So 3 times log base a of x minus 5 over 2 logarithm base a of p minus 4 times the logarithm base a of q. So as I noted, you could have just taken this 1/2 and moved it out in front. And if you did so, you would have 1/2 times the logarithm base A of x to the 6th, p to the 5th, q to the 8th. And so then if we expanded that, the 1/2 stays out in front, but it belongs to everything. So you would get the logarithm base A of x to the 6th minus the logarithm base A of p to the 5th minus the logarithm base A of q to the 8th. We then move all of their exponents out in front. So we have 1/2 times, and we have 6 times the logarithm base A of x minus 5 times the logarithm base A of p minus 8 times the logarithm base A of q. And then finally, if we distribute our 1/2 in, 1/2 times the 6 is still 3. 1/2 times -5 is still 5/2, or -5/2. And -8 times 1/2 is still 4. And we notice that's the exact same answer we got doing it the other way, right? So the reason I want to mention this is if you're working with some other people while doing your log properties, there are millions of ways to get from A to B. As long as you don't break any rules using your exponential and log properties, you will get to the correct answer. So there is not one way to go from A to B. So you can do this problem completely different from someone else, but you should always end up with the same answer at the end, regardless of the path that you took as you moved forward. All right, let's take a look at our next examples. So we're going to switch gears here. So for the first several examples, we were taking things that were one logarithm and making them into many logarithms. Well, anytime we learn to do something in math, we also need to know how to invert it or undo it. So based on some of our observations from above, we noticed inside our logarithm, things that were in the denominator ended up with minus signs, and things that were in the numerator had positive signs. So taking a look at these three logarithms, positive, negative, and positive. So we're going to have one thing in the denominator and two things in the numerator. Before we can apply either the product or quotient rules, we need to move all of our exponents back in. So we will move all exponents, or all factors, so turn all products into exponents. So we're going to have our logarithm of x plus 2 to the 5th minus our logarithm of x plus 1 plus our logarithm of x, and that product turns into an exponent. So now by our product and quotient rule, we're going to end up with log, and in the numerator we have x plus 2 to the 5th times x to the 4th all over x plus 1. Our negatives going to the denominator and our positives staying in the numerator. All right, example 9, we want to do the same thing. The only difference this time is instead of nice whole number exponents, what do we have? Fractions. No big deal, right? Everything works pretty much the same. So x minus 5 to the 1/3 minus the logarithm of x plus 4 to the 3/4 minus the logarithm of x plus 2 to the 1/2. So now I have two negatives, and that's going to give me the logarithm of x minus 5 to the 1/3, and then in the denominator, x plus 4 to the 3/4, and x plus 2 to the 1/2. So then, we normally, by convention, don't leave fractional exponents, so we would write it as the cube root of x minus 5 over the 4th root of x plus 4 cubed times the square root of x plus 2. And that's just converting all of our fractional exponents back into their radical form using our fractional exponent rule. So remember, the index comes from the denominator in each of these. So our 4, and with square roots we know the index is 2, so we don't write it. And then our numerators become the powers on the radicand. So we had a 3, so that's a 3. The other two had powers of 1, so we don't write powers of 1 because anything to the first power is just itself. All right. So we take a look at example 10, and you're like, okay, it's more of the same, right? We've got 1/3 natural log x plus 3 natural log x minus 2 natural log x. So you're like, okay, I've got some positives and some negatives. I'm going to do the same thing and put all my exponents up. Sure, so let's do that. So we do the natural logarithm of x to the 1/3 plus the natural logarithm of x cubed minus the natural logarithm of x squared. So then, using our rules, that's going to be the natural logarithm of x to the 1/3 times x cubed all over x squared. Oh, well now I'm multiplying things with the same base, so I can just add them up. So that gives me, in the numerator, 1/3 plus 3 is going to give me 10/3. 1/3 plus 3, we make 3 into a fraction over 1. That gives us 9 plus 1 is 10, so 10/3 all over x squared. But then, we're now dividing two things with the same base, so we subtract. So that gives us 10/3 take away 2 is going to be 4/3. And 10 over 3 take away 2, multiply by 3 over 3 gives us 4/3. So then as our single logarithm, we could then write this as the natural logarithm of the cube root of x to the 4th, and one could argue that that could be simplified. So you might be thinking, well, man, that seems like a kind of strange that it's simplified on the inside. None of the other ones did, right? Why did that happen? Well, it turns out because we didn't need to use any log properties at all. Going back to the original problem, what do I have? ln x, ln x, ln x. We didn't need to use log properties. These are like terms. Right? It says 1/3 x plus 3 minus 2. So if we gather up our like terms, what are we going to end up with? Well, in other words, what's 1/3 plus 3 take away 2? Well, we've seen that number somewhere before. 4/3. So then I would end up with 4/3 times the natural logarithm of x. Well, then if I move that to the inside, I get the natural logarithm of x to the 4/3, which is then exactly the same answer that we had before. Which one of those was easier? Definitely the second method, right? So be aware that there can be things that look like we need to use log properties. If they're all exactly the same, they're just like terms. Just add them up or subtract them as you normally would. Don't go through the whole log thing. Once again, if you do you get the wrong answer? No, you just spend a lot more time getting it than you need to. It's not wrong, it's just more difficult. All right, so let's go ahead and resolve this. So a couple of different ways we can do that, but let's start with our quotient rule. So if we use our quotient rule, we have the logarithm of x squared minus 5x minus 14 all over the logarithm of x squared minus 4. So we have two quadratic polynomials, and we can factor each of them. So x squared minus 5x minus 14 are factors of negative 14 that give us negative 5 are x minus 7 and x plus 2. And in the denominator, it's the difference of squares, so it's x minus 2 times x plus 2. After doing so, these two things reduce out, and we are left with the logarithm of x minus 7 over x minus 2. So we can express it as a single logarithm and simplify out some factors, right? So that's probably the fastest way to do that problem. There are other ways. If we factor first, we would have the logarithm of x minus 7 times x plus 2 minus the logarithm of x minus 2 times x plus 2. Then each of these are factors, right? So we could use the product rule. And that would give us the logarithm of x minus 7 plus the logarithm of x plus 2 minus the logarithm of x minus 2 minus the logarithm of x plus 2. And we have this and this are equal but opposite, so they add to 0. And then by the quotient rule, we end up with the logarithm of x minus 7 over x minus 2. Exactly the same answer we got doing it the other way, right? So this is what I was talking about with these problems. There's tons of different ways to get from A to B. So you may find different ways to do them, and that's fine. As long as you don't break any log rules, knock yourself out. There's all sorts of paths to get around. So like I said, I think this one's a tiny bit shorter than this one, but it's really not much shorter. So it's not like it saves you 10 minutes or anything. All right. The next thing I want to talk about is the change of base formula. So it's in that table at the very front of this, but we should mention it. So the change of base formula tells us how to change the base of any logarithm to any other logarithm. So change of base formula is this guy right here. Tells us that we can change the base of a logarithm base b of m is equal to the logarithm base a of m divided by the logarithm base a of b. We're like, well, that's nice. So we can change a logarithm of any base to a logarithm of any other base. It turns out, since our calculator has, every scientific calculator always has two logarithm buttons, namely the natural log and the common log, why don't we let a equal 10, and we're going to let a equal to e. If we let a equal 10, we get that the logarithm base b of m is equal to the log of m divided by the log of b. And if we let a equal e, we get that the logarithm base b of m is equal to the natural logarithm of m divided by the natural logarithm of b. So those are helpful because every scientific calculator will always have those two logarithms available for us to use. So let's take a look at our last example. So we want to find the logarithm using the change of base formula. So let's go ahead and change our logarithm base 6 of 999 is equal to either the logarithm of 999 divided by the logarithm of 6, or it is also equal to the natural logarithm of 999 divided by the natural logarithm of 6. So let's go ahead and compute that on our calculator. So if we go log 9999 and over log 6, we get this number. And if we do the same thing again, but this time with the natural logarithm, so the natural logarithm of 999 over the natural logarithm of 6, we also get the same value, right? Okay. So we can change to any other base we wish using this formula. For practical purposes, the most useful things to change to are 10 and e for our bases, although there may be occasion we want to change to other things. All right, so if we change our base, we have the logarithm base 4 of 275 can be equal to either the logarithm of 275 over the logarithm of 4, or the natural logarithm of 275 over the natural logarithm of 4. So once again, putting either or both of those into your calculator, we will end up with the following. So we have log 275 over log 4. And if we do the natural logarithm, we'll see that we get the same thing. So once again, we get 4.05 in either case. So in the interest of full disclosure, your TI-84 actually has a new and an improved logarithmic button that not all scientific calculators have. So if you don't have access to a TI-84 but just a scientific calculator, this is plan A. So we also may need to change the base of a logarithm when there are variables present and not just constants, in which case you have to use the change of base formula because you can't put them into your calculator. But now, if we take a look if we press alpha and window on our calculator, it should pop up a menu that looks like this. If you look at choice number 5, you will see that it says log base. You go down and select it, and it now inserts a logarithm where we can actually just type the base in. So 4, right arrow, and then 275. Press enter, and our calculator gives us this value. So essentially, they just pre-built a function into your calculator that does the change of base formula for you. So that'll be helpful for some of these things like this, where you're just trying to compute a number. We may still need to use the change of base formula, like I said, if any of our things are variables, like the argument of the logarithm. You obviously can't just type that into your calculator.